Hello everyone, welcome to Nrcm, and this is Shravani, and I'm going to speak about the subject called as operating system of Unit 2, and the topics are today's discussing topics are round robin, multi-level queues, and multi-level feedback queues. So first of all, coming to the round robin. So what happens in the round robin, as we all know that it is a scheduling algorithm, and here in the round robin some fixed time is allotted to each process, and this fixed time is called as quantum, and which is used for this execution. Okay, and here the processes are dispatched in first out manner, but they are given a limited amount of CPU time, which is called as the time slice. So here time slice in round robin, the time slice or time quantum, you can call it as time quantum, so it is very important. So and if the process does not complete before its CPU time expires, the CPU is preempted and given to the next process which is waiting in the queue. The preempted process is then placed at the back of the ready queue. So normally this round robin is like, say if you are waiting for any of the store, and the store manager has given the time quantum or time slice like only up to 2 milliseconds or 3 milliseconds. So there are so many people who are waiting in the queue. What happens? So the first person is in the queue will be executing, will be taking some groceries, and once the time is finished, so the manager will not take his request. So but this groceries, if this groceries list are pending, so the same person will be coming back and he'll be again standing in the queue. Okay, and next happens with the next same second user. He will be approaching the store manager. The store manager in this, he will be approaching for the grocery store again, and within the time quantum, so if he gets all the groceries means he will go back to home, else again he will be waiting in the queue if any of the pending groceries are yet to be purchased means. Okay, the same happens with 3, 4 and so on. So this is simple, this is a round robin. So coming to the example, like here how many processes are there? 4 processes are there. Okay, and coming these 4 process, and it takes the burst time, like process P1 wants 21 milliseconds, P2 wants 3 milliseconds, P3 wants 6 milliseconds, and P4 wants 2 milliseconds. So all the process has been arrived in the ready queue, they are waiting in the ready queue. Okay, so the here the scheduler will select the processes based on the first come first serve, but only the difference is, so if you understand the first come first serve, which I have explained in the previous video, so then this round robin is very easy, and only thing for first come first serve, you need to just attach the time slice. Okay, the time slice or time period will be given. Okay, so until the time period, so consider here the time slice we have taken, it is like 5 milliseconds. Okay, consider it is 5 milliseconds. So first in the queue there is P1 is there, P1 is present, so P1 starts executing. So until it completes its time period, so it will be executing. So then, so once the time is finished, then the CPU switches, or then CPU brings this P2 and it will put into the queue. And again this P1, what it will do, it will go and wait in the queue. Okay, P1 will be going and waiting in the queue. Next, once the P2 is executed, okay, P2 is executed. So first P1, P2, P3, P4, all will be placed in the memory. Okay, all will be placed in the memory. So here, what happens? P1 it executes until its time period, and if the the burst time, or if the total time is not been completed yet, it has still some it has still some execution, or execution is pending, then it will go and stand in the queue. Next, here considering the time slice as 5, we consider, so it executed up to 5 milliseconds, and remaining it is in waiting stage. Next, coming to the P2, so as given time is like 3 milliseconds, but it doesn't require 3 milliseconds, so this P2 it completes its execution, and it moves out from the memory. See here, there is no P2 in the there is no P2 in the queue. Okay, next coming to the P3, that time quantum is taken 5, but it requires 6 milliseconds, so it executes up to 5 milliseconds, and again it will go and stand in the queue for to execute remaining the time. So okay, next is coming to the P4. The given time slice is 5 milliseconds, but it doesn't have that much of work. So within 2 milliseconds only it has finished its work. So this P2 has finished its work 2 milliseconds and it has vanished from the memory. Okay, now which are in the queue like P1 and at P3. So again P1 starts executing, so up to 5 milliseconds and again go to the wait stage. Next P3. So coming to the P3, it executes its program up to 1 milliseconds and then it will be vanished from the memory. So again P1 will be executed. So this continue. This happens. The P1 has been executed until it has completed it has completed 21 milliseconds. Okay, this is all about the round robin. So and the average waiting time will be calculated. Like for P1, what is the average waiting time? That is 31 milliseconds. So you should start calculating from right to left. Okay, so for P1, the average waiting time is 31 milliseconds, and for P2, where is P2? The average waiting time is 5 milliseconds, means at 5th millisecond it has got the chance to execute the program, and for P3, it has got 20 milliseconds. Okay, and P3, and next for P4, and where is P4? So you should check from here. So for P4, it is 13 milliseconds. Okay, this is all about round robin, and I hope you all understood. Next, coming to the multi-level queues. Here, the multi-level queue, here, what happens here? The process. Normally, the processes which are in the ready queue, they can be divided into different classes, where each class has its own scheduling needs. So, coming to the, for example, common division, there will be some processes which will be executing in our coming to the speaking to our computer only. There will be few processes which will be executed in foreground. Okay, and there will be some processes which will be executed in background. Okay, these two classes have different scheduling needs. For this kind of situation, this multi-level queuing is scheduled. Okay, this is simple. Suppose, this happens all within the one computer, and the system process is having the highest priority, and then interactive process, and then batch process, and so on. Okay, suppose, in multi-level queues, suppose the system process uses some FCFS algorithm, and this interactive process, consider it uses some SJF algorithm, and round robin, it uses some priority algorithm. Okay, in multi-level queues, like different queues can be, they can use the different algorithms. Okay, but the main, if you observe, the system process queues, but all the queues will not be executed at same time. So first of all, the highest priority queues will be executed first. So here, the which is having the highest priority, the system processes are having the highest priority. So the processes which have entered into this system processes queue will be executing first. Okay, and then interactive process, and then like basic process, and then batch processes will be executing. Okay, what did you observe here? So everything is fine. We can assign different algorithms to different for different processes, but the disadvantage is like the starvation. Okay, this multi-level queue, it suffers from starvation. Starvation is like, suppose if there are different n number of the processes which are of a system process. Suppose there are there are 100 processes. Here there are 2 processes, and here in batch process there is like 3 processes. So until this 100 processes executes, then next interactive process, next it won't come to the interactive process. So the 2 process should be in waiting state. And until the 2 process 100 plus 202 process execution is completed, so next the batch process time will not be started for execution. So here the processes will be in starvation mode. Okay, suppose for example, in it has completed, like execution is completed. Here there are 0 process and there are 0 process. Consider here batch execution has been started, batch processing has been the priority based schedulings, they are started executing here. In the sudden, or in the middle of the execution, or after the middle of the execution, some new process has arrived here to the system process. New process has been arrived. Then what happens? The whichever the process are executing in this batch processes, it will be paused, and then the operating system will take this process for, it will consider this process for execution. So that is the main drawback in this multi-level queue. So to overcome the drawback, I mean, like we are considering this multi-level feedback queue scheduling algorithm. So here what happens? So multi-level queue means scheduling algorithm. It can mean the process can move between the queues and it is efficient than the multi-level queue scheduling. So how? Means suppose consider here there are Q1, in Q1 there are few processes, Q2 there are some more, and Q3 there are some more. So in Q1 consider there are, I mean, it is using round robin schedule and the time quantum is like 4, and Q2 the time quantum is 5, and remaining it is using the remaining third queue, it is using FCFS. There is no need of the time quantum. So suppose if there is a process P1 which has arrived here, and there is a process P1 which is arrived here, and it wants execution, and as it is a round robin schedule, it wants time quantum. Suppose here consider its time quantum is like 15. Consider its time quantum is 15. So here what happens? So time quantum is 50 means up to 15 milliseconds. So after up to 15 milliseconds for this all over round robin, up to 15 milliseconds this process should be executed. Okay, and time quantum is 4 here and time quantum is 5 here. So let us consider this 15 as a burst time. So up to 15 milliseconds it should execute. It wants the CPU. So but here in the coming to the Q1, so it can gives only 4 milliseconds of time. So what it will do? So it will execute up to 4 milliseconds of time. So and then so again it will pass to the Q2. Okay, it executes up to 4 milliseconds, and remaining like 15 minus 4 is remaining 11 milliseconds are pending. So if it, this process P1 will be get terminated after 11 milliseconds. So here what happens at, and remaining this 11 milliseconds, it will try to execute here. But what happens here? The time quantum is only 5 milliseconds. So up to 5 milliseconds, it will execute in the second queue. And then once the time quantum is finished, then again it will be moving to the third queue. So that is, so remaining, so 11 minus 5 is like up to 6 milliseconds, up to 5 milliseconds it will be executed, and remaining 6 milliseconds of time should be required. So here remaining the 6 milliseconds work will be executed in this, this Q3. So this is multi-level feedback queue. So and this is the advantage is like if there are n number of the processes, if process P1, P2, if there are n number of the processes, consider P1 and P2. See here, P1 first arrived in Q1, Q2 and Q3. So in the meanwhile, so P1 once it leaves the P2, Q1, so next this P2 will be entering into the queue. Okay, so that is the advantage here. Like it is efficient, it is more efficient than the multi-level queue scheduling. I hope you all understood the topics, dear students. And if you are having any doubts, you can ping me. And next, the last point is like system call interface for the process management. For every process, as we discussed in the unit 1, we'll be having different system calls. For every system also, for every operating system, there will be different system calls and few important system calls for the process management. So first is wait is the system call. So this wait is used, if the wait system call has arrived, a process may wait for another process to complete its execution. Means if the process is in waiting stage, then the wait system call will be generated, and we can say like if the parent process, if the child, if there is a child and parent process. Okay, if the parent until the parent child process completes its execution, the parent process will be going into the, or it will be going into the waiting stage, or you can tell it will be going into block stage or suspend stage. Then the wait system call will be activated or generated to the parent process. Next is execution. Execution, as you all know that this is the system call which runs an executable file. Okay, it runs some executable file. The process is executing, then this executing system call will be generated, and it is also known as the overlay. Once the process completes its execution, so once the process it's completes its execution, the process will be replaced by the new process. Means the execution parts, what are the things like data, heap, stack, everything whatever will be assigned to the process now, that will be assigned or replaced by the new process. And next, fork. As we all know that fork is a system call. Fork is a system call which is used to create the processes. Means it can create a process by itself and it can create the copy of process or child process also. Okay. And see, if once in the, as we all know that discussed, the if the child process is executing, so then parent process will be in waiting stage. So when the child process completes the execution, then only the parent process will start executing its process. Okay. And next is exit. Exit is like it is a system call used by the program to terminate the execution. If you want to terminate any of the execution, so I mean, it can use this exit. I mean this exit system call. Normally in multi-threading environment this happens. Next is kill. Kill is like this is the system call which is used by the operating system mean to terminate the process. Kill is like once a process completes its work, so this will be terminated. The process will be killed by the operating system and the new process will be given the chance for execution. This is all about system call interface for process management. Okay, thank you.